Okay, thank you. I think I was just going to be talking to myself and realize after an hour that I have been unmuted. So let me just repeat what I said. Um, or maybe, so I said that in this lecture, I've given you more problems for where you will be calculating the differential cross section. So in this problem that I gave you, I've just given you v of r to be v0 e to the minus r over r. This potential is referred to as the Yukawa potential. And what I'm asking you to calculate then will be go ahead and calculate the differential cross section and also the total cross section. So the differential cross section, we had derived a formula, so d in the Born approximation, so d over omega. So what we did in the last lecture is that we have always assumed that v was very small and also that it had a finite range. And in that approximation, we derived a formula. This formula for f that is given by f of theta will be, I cannot hear you. I'm not muted. You still, someone can hear me. So let me just check. We cannot hear you. Can everyone hear me now? Okay, fine. So I was saying that the general formula that this formula will be quite general. So once you have determined what the form of that function f of theta will be, then you know that if you take the absolute value squared of that thing, that will give you the differential cross section. But in the Born approximation, this we found that this was given by 4 mu squared over h bar to the 4 q squared integral from 0 to infinity r prime v of r prime sine q r prime dr. I think it's the absolute value. So this will mean that we have to first compute that integral in order for us to be able to get what the differential cross section will be for the Yukawa potential. So let's go ahead and compute these types of integrals. So you have to integrate 0 to infinity e to the minus r over r. So this is just v of r prime, but you still have to multiply this by sine qr and then integrate. So to do these types of integrals, you use the same trick that I gave you in the test. So you write sine of z will be given by 1 over 2i. You write to a trig function in terms of exponential, so this will give you I to the z minus e to the minus iz. So you just take this, plug it there. So this will split into two terms. You get 0 infinity e to the minus r. Okay, I've already done the integral. Let's just do everything step by step. So you get e to the iqr minus e to the minus iqr over 2i. So this gives you e integral 0 to infinity e to the minus r over r plus iqr minus e minus r over r. And I see that once you do these integrals, you get 1 over 2i. The 1 over 2i is coming from the definition of the sign. It's that term there. These integrals just give you 1 over r minus 1 over q. And I think even in the last question in the test, I think everyone got this step, but I prefer that you add these two fractions and write it in terms of a real number. So once you've simplified and done the algebra, this just gives you q over 1 over r squared plus q squared. And then you just plug this into the formula for the Born approximation. We've calculated that. So we found this integral was given by q 1 over r squared plus q squared. So I think one of them will cancel there. And just simplify everything. So that's what you get. And I derived that relationship between q and sine theta over 2. So you because so far what we are doing is that we're dealing with elastic scattering. So just plug everything there. So that then the total cross section. So to get sigma, you have to integrate d sigma over d omega and the differential area or the solid angle d omega is given by d theta, d phi sine theta. This will not be depending on phi, so you can do the integral over that. So this gives you 2 pi d sigma over d omega of sine theta d omega. So then you change variables. So I did that in the next slide. So I think everyone should be able to do that. You change then variables, and this integral I think you can do, and that's the answer that you get. Find the potential for elastic of mass m initially traveling in the double potential. Let's see. So the next potential that I gave you was a double potential. So you have to write what that potential would be. So this is V of R given V naught delta R minus A K plus delta R plus A K. So this is the form of the potential. So again, just plug it into the formula for the Born approximation. So d sigma over d omega is going to be given by m squared over 4 pi h bar squared h bar to the 4 integral v naught delta r minus ak plus delta r plus ak vector d3r eiq dot r. Right. So let me just write everything. It's 4 pi h squared squared I squared. Then the integral I will just be integral over x, delta of x ei x qx. So the only thing, because it's only depending on that k, the only integral that you have to worry about would be the integral over z. So that integral then splits into delta z minus a plus delta z plus a, and then e I z q dz. I think these integrals are just one, so the only integral that you have to compute then would be the integral over d3, not d3z, but only one-dimensional integral over dz. And that, okay, let me say this, you can check, it's going to be given by iqz plus e to the minus iqz, and this, you make use of these identities. You can write it directly in terms of the Euler identity. E I z is given by cos z plus I sine z, or by definition, the cos function. I've been giving you this definition for cos, so this just gives you 2 cos q z, and q we found an expression for in the last lecture. So qz, just q proportional to this factor of sine theta over 2. So this gives you 2k sine squared theta over 2. And then you just plug everything into the formula. D sigma over d omega is going to be m squared v naught over pi squared h bar to the 4 cos squared 2qk sine squared theta over 2. And, yeah, so those are the examples that I've added from the last lecture. But today we are going to be looking at another method of computing the differential cross section, where The only difference is that in this case, it's going to be quite general. So we are not going to be making any assumption about the strength of the potential. So we are not going to be saying that the potential was small. And in order to do this type of computation, they all rely on an identity. So the identity is, but I'll try to sketch how you will prove this. So if you remember, you first write psi as E as phi incident plus phi scattered. So phi incident will just be a planar wave. So you have some target and you send waves, and some of the waves will not be scattered, but some of them will be scattered through some differential, um, some solid angle d omega, and phi incident will just be the solution. So at that region there, which is far away, and also at that region, the Schrodinger equation will just be for the free particles. So the solution will just be given by free planar waves, eik dot r, and phi incident we wrote it as ikr over r with some function f of theta. You could assume that it was f of theta and phi. But the point was that the incident was given in terms of that. So the idea behind the partial wave is that you try to write this in terms of IKR. So let's just say that you choose your z-axis to be, so let's just be IKR cos theta. And then there's this identity. So this will be given by, and this is the identity that we are going to be making use over and over again. So I'll try to first sketch the proof. So this gives you 2L plus 1 I to the L. And then it's written in terms of this equals to 0 to infinity. J spherical Bessel function, K of R, and then PL cos theta. So this is the identity that we are going to make use of. So the idea is that you take this identity, you plug it into that expression, then you try to determine what the form of f of theta phi would be. Once you've determined that using this expansion, if you take the absolute square of that, then that will give you the differential cross section. So first thing will be to try and check how you do that identity. So if you remember the Helmholtz equation, or if it's given by del squared plus k squared psi, let me just call it psi, it's equals to 0. You can see that psi is going to be depending on some radial and maybe Lm of theta and phi. The radial part of the equation will be d2r over dr squared plus 2 over r dr. It's just usual separation of variable technique. So let's say v minus l plus 1 over r squared, r is equals to 0. And this equation, the Bessel function, the solution can be written in terms of Bessel function. So the spherical Bessel functions are defined to be, let's say, z small capital or small letter z as a function of x. It's going to be given by square root of pi over 2 z. They are the usual Bessel function, but shifted by, instead of them depending on the integer, they are half integer. So x over square root of x. And then the radial wave function, say it's labeled by L, which is that label there as function of R. So it's a second order differential equation. So it will have, can be expressed in terms of two functions, or JL of KR plus B, and this will be the Neumann function L and KR. But if you are going to include the origin r equals to 0, you find that this function, the Neumann function, diverges when you take r to to 0, and we are interested in what happens at r equals to 0 because that's where our scattering occurs. So maybe you are saying that this is minus infinity, where the potential is so r less than a, between 0 and a. So that part there vanishes if you're including r equals to 0. So that means that any solution of the Helmholtz equation can be expanded in terms of this function, of those functions. So psi can be written as a k or l l m j l k r y l m theta and phi. I'm just saying that these functions are complete. So any function, including the solution to the Helmholtz equation, can be expanded in that form. The simplest solution to the Helmholtz equation will be the form psi k is given by a e I k dot r. It's very easy to see that this is a solution to this equation, squared plus k squared psi k, because once you differentiate twice, this will bring down an ik, so you get I k dot k ik plus k squared. So this gives you minus k squared plus k squared, which is 0. So this is a solution to the Helmholtz equation. So it means that it can be expanded in terms of the spherical Bessel function. So let's just call the coefficient al j l k r. Usually there's going to be a spherical harmonic sitting there, but you have to choose L0. Right? Why did I choose L0? It's because I'm writing this as EIKR cos theta. This function does not depend on phi, right? So, and YL of 0, this is just PL of cos theta. So you can expand EIK dot as AL, JL, KR, PL cos theta. Now you have to determine what this function or what these coefficients are. So to do that, you multiply everything by, okay, let's just change variables and call r, let's just call cos theta. I'm sure you've seen this. You can call it x, or I'll choose to call it u. So you get E I K R U is given by L J L K R P L cos theta. Right? So the first thing that you do is that you multiply everything by P n of u, and then try, so let's say P n of u, and then try to integrate between -1 and 1. Integrate between -1 and 1 of du. Let's see what we get. So delete. So on the left hand side, let's just write what we get. You get -1 to 1 of Pn u E I K R U du will give you integral AL JL. This just depends on the radial part. So you still have to integrate -1 to 1 of Pn of u PL of u. Right, we still have to sum through L du, and these functions are orthonormal. So I think they give you these ones, they give you 2 over 2n plus 1 delta n L. So then this sum only reduces to only one contribution. So you get that this gives you a n j n k r 2 over 2n plus 1. So you can sort of get what the coefficient expansion will be. The problem is that you still have to do these types of integrals. So you get that an will be given by 2n plus 1 over 2 Still have to do the integral minus 1 to 1 Pn view EIKRU du. What I'm trying to write, so delete. Right. So then you then consider what happens when k goes to 0. So these spherical Bessel functions, Jn, for small values of kr, they behave like square root pi over 2 kr over 2 to the n, 1 over gamma function n plus 3 over 2. So then the only contribution will be coming from m equals to n. So you get a n. That other integral that I gave you, you can check that minus 1 to 1 of Pn of u un du will be given by 2n plus 1 n factorial squared over 2n 1 factorial. So once you plug everything into the expression for an, you get an square root pi over 2 kr over 2 to the n 2n plus 1 n factorial over 2n plus 1 square root pi, and then the expression on the right hand side is just similar to n plus 1 over 2 in kr n over n factorial, and then you make use of that expansion, so you get 2n plus 1 n factorial over 2n plus 1. Right. Most of the factors are going to cancel. For example, kr over 2, there's a kr, and the only term that will be left will be this one there. I think that in there, so you can automatically solve what that an would be, and you find that an will be, let's see where, I n 2n plus 1. So we are done. So we have proven that EIKR cos theta is going to be given by what I called an. We've just solved what that expansion coefficient would be. So just let me use L from 0 to infinity, IL 2L plus 1. We still have JL of KR, and then the only thing, usually it's going to be a spherical harmonic, but because it doesn't depend on phi, we just put PL cos theta, PL of cos theta. This is the expression that we're going to use. So from the lecture on Tuesday, we showed that psi of r and theta are going to be given by, let's say, their solution to the Schrodinger equation. So there will be some expansion parameter r k l y, but because it's not depending on phi, this will just give you pl of cos theta, and the radial part you find by solving the radial Schrodinger equation. So d2 over dr squared plus k squared minus l plus 1 over r squared. R, let's say you've done this even for the hydrogen atom, it's going to be r multiplied by rkl. This gives you 2m over h bar v of rkl. It's a function of r. But on Tuesday, I also showed that whatever solution that you get, is going to be a superposition of the incident wave function, which will be just e. Okay, I thought someone was saying something. EI k r at cos theta. This is just the incident wave function plus the scattered one, which will be EIKR over r multiplied by f of theta. and we've just derived an identity for that. So you plug that identity into that expression. So this gives you E I L of 2L plus 1 JL of KR PL cos theta. Still have to sum. So I've done nothing fancy. I'm just using that identity that I proved. So instead of writing EI chi R cos theta, I just expand it in terms of spherical Bessel function and also the Legendre polynomial plus EI k R over R f of theta. So I've not really done anything fancy so far. Now the fancy thing then will come from the fact that for scattering events, we are always looking at, it's like the detector is placed at R equals to infinity. So we have to look at the behavior of these functions, which is where we are measuring the differential cross section at. So we have to look at what happens, how this function, the spherical Bessel function, behaves when we take kr to infinity. So it's an identity. So you know that JL, KR, asymptotically, it behaves like a trig function. So this just gives you sine KR minus L pi over 2 divided by KR. So then you just plug this into the expression for psi of R theta. It's going to be a sum over these JLs, but instead of writing the JLs, because now you're looking at the asymptotic behavior, you write it in terms of the trig function. So this just gives you IL 2L plus 1 PL of cos theta. And then the spherical Bessel function, you replace it by sine KR minus L pi over 2 divided by KR. But there's still that other part KR over R f of theta. And then you do what I've been doing. You write the sign z in terms of the exponential, EIZ minus EIZ e to the minus IZ. Right? So this will give you a vector e to the I. Let's just maybe try and simplify something. So let's say that you first look at sine kr minus L pi over 2. You make use of that identity there. So this will give you 1 over 2i minus 1 to the L EIKR plus, oh, it's a minus 1, I think it's I, plus I to the L e to the minus IKR. So I've made use of the fact that once you try to expand, it's going to be an exponential of z, so it's going to be an exponential kr, which is that part there, but you still have an exponent over plus or minus I L pi over 2. Write this as E I pi over 2 plus or minus. There's still that L, so this gives you plus or minus I to the L, which is this vector sitting there. So you then group the like terms. So the e to the I minus IKR, there's only one term, whereas with the IKR, there will be a term coming from that sum plus also that one. So in the end, everything simplifies to that the wave function psi r theta gives you e to the minus IKR over 2IKR sum L I to L plus 1 of PL cos theta. But the positive exponential will have two contributions, so you get 2, just call it R, Right? There will be the term coming from the scattered wave, which is just f of theta, but there will be the other term coming from the sum. Once you've written the sign in terms of the exponential, so that other one will just give you 1 over 2 ik sum L going from 0 to infinity, IL minus IL 2L plus 1, let's just call it PL. Right. Now, because you're looking at the region R going to infinity, then the radial equation, you know that there's going to be a term like R plus 1 over R squared. You can ignore that one, so the only one that you're left with will be d2R over dr squared. Also the term that will have an 1 over R, because the detector is sitting very far from where the scattering actually occurs. So the only term that will be left will be squared R. So this equation, as I've been saying, you can solve it in terms of the spherical Bessel function. So this gives you, let's call it AL, JL of KR. But there's going to be let me write it, the other solution, which is the Neumann. Right. Now, I've told you that this behaves like sine once you are taking R to infinity. And you can check that the Neumann function behaves like a cos. So the radial equation or wave function, then asymptotically it will behave like AL of J, but J is just behaves like sine KR minus L pi over 2 over KR. Similarly for B, BL of KR of cos KR minus L pi over 2 over KR. Now you're going to make a trick that, let's assume, I'm sure you've seen this, so we're just going to assume that you can write this in terms of a single trig function, right? So let me choose sine of KR minus L pi. So this will be an unknown that you have to solve. And the other unknown would be this phase shift delta, so over KR. So how do we then solve for these unknowns? If you go back to the equation from high school for sine A plus B, just make use of that one. So this will give you, let's just simplify that equation by ignoring the KR for now. So this will give you CL of sine KR minus L pi over 2 cos delta L minus CL cos KR minus L pi over 2 sine delta L. So this, then you can read off what CL multiplied by cos delta L, because you're comparing that coefficient there. So the sine KR minus L pi over 2 are the same. They're the same. So this means that CL cos delta L is going to be given by your, what I call AL. And similarly, CL, that CL multiplied by sine. Remember that the unknowns here are CL and the phase shift delta L. So this gives you sine delta L will give you, and then you're comparing, so it has to give you that coefficient minus BL. So these two equations you can solve. So if you just square those equations, a squared plus BL squared, this gives you CL squared of cos squared delta L plus CL squared sine squared delta L. Right? So that will give you 1, or I'm saying that just factor out the CL squared, cos squared, and sine squared give you 1. So you already know that what that CL will be is just the square And similarly, if you divide equation 1 by 2, you get 10 delta L will give you minus BL over EL. So let's see where I wrote everything down. Um, mm, um, it's there. So you've just shown that AL is given by that, BL is given by that, and this is just called the phase shift. So go back, use an empty slide. So we have shown that psi, r, and theta can be expanded in terms of some unknown coefficients, p, l, cos theta, sine kr. This is what we've shown, L pi plus delta L, where this delta L is just given by the 10 or up 10 minus 1 over kr. Right. You make use of the same trick, right? You write sine z in terms of exponentials, and then you use the fact that ei pi over 2l. This just gives you plus or minus I to the L. To rewrite this expression, then you group the terms that will be coming with positive, the positive form of the exponential. So this gives you e I k r over 2 I k r a l I l, which is this I l there, cos gotten rid of the trig function I delta L PL cos theta. Let's just say start with the minus 1 plus EIKR over 2IKR AL minus IL EI delta L PL of cos theta. This is another expression for the wave function, but we had initially, once we plugged the form size phi incident EIKR, expanded everything in terms of Bessel functions, we found that the wave function could also be written as e to the minus ikr over 2ikr times of I to L plus 1 PL plus there won't be any space, but we had an f of theta plus another contribution coming from the sum. So then we just compare the coefficients of these two expansions. So that will give us what is AL. And also from AL, then we will be able to determine what is f of theta. And once we have f of theta, then we're done, because once you take the square of f of theta, that will give you the differential cross section. So once I started comparing those two results, you find that AL, this function AL, is just going to be given by 2L plus 1 EI delta L IL, and f of theta plus 1 over 2 IK sigma IL minus 1 L 2L plus 1 of PL of cos theta. Right. This, once you compare it with what will be left in on the other side of the equation, we just get 1 over 2 IK sigma 2L plus 1, and we are nearly done, because this is what you're looking for that f of theta. So we get IL minus I to the L e to I delta L, and this e to the I to delta L, let's try and simplify it to delta I minus 1. Uh, I think I'm I'm skipping a step. You're going to solve that f of theta, so it's going to be given as a over L. So you get f of theta. It's going to be sum L going from 0 to infinity. I'll just call these functions f of L, whatever I'm summing over, which are going to be the partial amplitudes. And I can solve it from this equation there. So you get 1 over 2ik 2L plus 1, the general polynomial of cos theta at e2I delta L, right? It's just that term, but the term on the left hand side is identical to the other one. It's just that it's coming, yeah, well, once you take it to the other side, it will come with a negative. And this, this term there, you can simplify it and write it in terms of sign. So I wanted to say that ei to 2I delta L minus 1 over 2. This gives you ei delta L of sine delta L. Or maybe I should try and motivate why that is. So if we've just seen that f of theta can be written in terms of 2I delta L minus 1. So I'm just saying that you're going to factor ei delta L. So this gives you ei delta L plus minus, just that minus there, e to the minus I delta L. Right. And this is just ei delta L to sine, right? We've been making use of these identities for a while, to delta L. So this means that we are done, because f of theta we found to be 1 over k sum L going from 0 to infinity, 2L plus 1. So the 2L plus 1 comes from expanding things in terms of spherical Bessel functions. Once we found those coefficients, they come up as 12 plus 1. And then we had that term there, which we will write as e to the I delta L. Missing a 2. There was a 2 there, so it will cancel that 2. Sine delta L. And then you still have to multiply this by the Legendre function. And we're done. This is the final form of the scattering amplitude. Just that I said that you can also write it as FL. So this is the scattering amplitude. These are called the partial amplitudes, which are just those coefficients there. And remember that once we have the form of F, then we can directly find what is the scattering cross section in this partial wave analysis. It's just the square f of theta squared. So we use dummy variables, so it's going to be sum over L prime. 1 over k times 1 over k will give you, good morning, the big number 6 is cut of the, I'll fix that. Let me just write so that I know which equation. Equation 6 slide 54. I'll fix that. So what you have on ClickUp is just the first version. I still have to also add the exercises which I didn't do. So I'll fix equation 6. So this gives you, so I was just saying that you just find these, okay, use dummy variables. So you get 2L plus 1 multiplied by 2L plus 1 prime, IL minus IL, see, I think EI delta L minus delta L prime sine delta L sine delta L prime, and you still have PL cos theta multiplied by PL cos PL prime cos theta prime. So you just take the expressions that I wrote, write the other one in terms of L prime, and then multiply them out. So it seems as if it's a messy expression, but the total cross section, for the total cross section, you have to integrate out over the angles, and then you're going to use the orthonormality of the Legendre polynomials. So d sigma over d omega, sine theta, d theta, d phi, nothing will be depending on d phi, especially because EIKR initially we had chosen our, it's just, it will be depending only on cos theta. So most of the things for the partial wave expansion depend only on the sine theta. So that other one will just give the integral over d phi will give you a 2 pi. So you get 2 pi, the sums are still there, L prime, 2L plus 1, 2L plus prime plus 1, EI delta L minus delta prime. The sine delta L prime, but the integral 0 to pi, you will be left with an integral. I won't write the arguments of the Legendre polynomials, PL prime, PL, let's just say PL multiplied by sine theta d theta. And because they are orthonormal, you can make use of the identity that delete. Let's see, what is the identity? So 0 to pi of PL of cos theta, PL prime of cos theta, sine theta, they are orthonormal. Sine, actually I've already made use of this identity, if you remember, minus when I was trying to find that coefficient AL is given by 2L plus 1. It's just that there I wrote it in terms of du, where u was just cos theta. So previously I had PL of u, PL of PL. Maybe I used an M, but it's the same identity, just that now you have written it in terms of trig functions. So this identity gives you 2 over 2L plus 1 delta L and L prime. So the total scattering cross section, which you can write as a sum over L over the L. So again, these are just called the partial total cross section, but partial total cross section. This, once you've done the sum, so this gives you, one of the sums will fall because of the Kronecker delta, so you're left only with the sum L going from 0 to infinity, 2L plus 1. There's a 2L plus 1 prime, which will cancel this factor there. So and then there was sine delta, so but you are setting L and L prime to the same, so you just get the square of sine delta L. Yeah, I think this simplifies. So I'm saying that the total cross section is simple. It's just given by 4 pi over k squared, sum L going from 0 to infinity of 2L plus 1 sine squared delta L. Yeah. And then you try to look at the imaginary part of the of f of theta, which is just this. So you set theta to be 0, and you're trying to find what is f of 0. This is just called the forward scattering amplitude, because it represents those waves that didn't really interact with the potential, so they just continued. So f of let's see, f of 0 will give you 1 over k. L0, you're just making, don't have the equation number, but EI delta, the expression that I got for f of theta, right? Sine delta L, but there's going to be PL of cos of theta. You're setting cos to be 0, so it's just PL of 1, which is just 1, so that's not there. Then you write this. So now I'm discussing what's called the optical theorem. Then you just make use of the Euler identity, so you get 1 over k L going from 0 to infinity to L plus 1. Let's say cos, okay, it's going to be I cos, because of that, let's just say cos delta L plus I sine delta L multiplied by sine delta L. So this gives you 1 over k L 0 to infinity 2L plus 1 cos delta L sine delta L plus I sine squared delta L. And remember that the total cross section proportional to sine squared delta L, or sum over. So if you look at the imaginary part, so this gives you that the imaginary part up to some factors, you can check that there are missing factor of 4 pi over k of the imaginary part of f of 0. This gives you the total scattering cross section sigma, which is 4 pi over k of the sum sine squared. So in summary, we have shown that the one way to get the total cross section, just multiply 4 pi over k of the imaginary part of the forward scattering amplitude. This will give you sigma. So far what we've been discussing is the elastic case. So the next case that we should discuss, or maybe let's see, maybe before I do that, let's just go through a simple example. So sigma example. So I'm considering this example. So it's a simple example, and you've actually measured the phase shifts. So delta is 95 degrees, delta 172, and all the rest are negligible. Then the question was find the total cross section and estimate the radius of the nucleus. So okay. And let me just think. So the rest of them are negligible, so they're basically 0. So for L, I will say greater than 6. So you just make use of the identity that I derived for sigma 4 pi over k squared. You sum over L equals to 0. And I think this is not in the slide, so I'll also add this solution. L going from 0 to 6. It's usually L from 0 to infinity, but the rest of them are negligible, so we only have to consider the first up until the 6th one. Then you just plug everything into the formula. It's proportional to sine squared delta L. So you just sum everything. So but we still don't know what that k squared will be. So you just get, and all I know is that it's a 50 MeV. That's the energy. So, but from that energy, I will be able to get k squared. So let's just sum everything. So you get sine squared delta 0 plus, then when L equals to 1, that gives you 3 sine squared delta 1 plus 5 sine squared delta 2 plus 7 sine squared delta 3 plus 9 sine squared delta 4 plus 11 sine squared delta 5. And these you have already measured experimentally, so just plug everything in there and you get 4 pi over k squared 10.702. And then you had already measured the energy. Let's just go back. it says that you're considering neutrons with 50 MeV. So from the energy, you can determine what is K. So K squared is given by 2 mass of the neutron E. And then you work in terms of MeVs. So I'll just multiply H bar by C squared 2mc 2mc squared, and the mass of the neutron and also H bar C, you can look them up in terms of MeV. So you just plug that, then 939.7 MeV. The energy was given to be 50 MeV, 197.33 MeV per Fermi squared. This works out to be 2.51 Fermi minus 2. And then you can then plug this into the equation for sigma. So the total scattering cross section 2.41 F minus 1 10.72. This works out to be 0.558 times 10 to the minus 28, and the unit for measuring cross sections is the bar. What else do we want? Because of time, I won't do the second part of the problem, but I was just trying to show you how you go about if maybe you measured these phase shifts, how you get the cross section for a realistic problem like neutron scattering. So the last thing that we could discuss was the inelastic case. So let's just rewrite what we found for the scattering amplitude. So f of theta, we wrote it as 2L plus 1 in terms of the partial scattering amplitude FL, which is again a function of f theta. Then we get PL of cos theta. So this function FL of theta, we found it to be 1 over k EI delta L sine delta L, but I think for this case it's better to go back to the original unsimplified expression in terms of e to the 2 I delta L minus 1 over 2 ik, which follows directly from that expression. It's just 1 over k EI delta L 1 over 2i EI delta L minus e to the minus I delta L. That term and that will give you the 1. Once you multiply these two, you get the term there. And we are just going to write this as 2ik, rewrite it. We're not doing anything in terms of this quantity as L of k minus 1. So for the elastic case, we know that as L, it's just going to be E2I delta L. So once we take the absolute value, this gave us 1 for the elastic case, but in the inelastic case, there might be energy loss or some certain flux might be absorbed by the target. So the simplest thing that might happen was that this SL of k gets to be multiplied by some function which is eta L, which is between 0 and 1. So and then once you set eta to be 1, that will correspond to elastic case. Once it's 0, that means that the entire flux is being absorbed by the target and nothing is being scattered. So let's see. So I'm just saying that I'm going to say that let's modify it by a fudge factor eta L of k e to the 2I delta L. Delete. So the partial amplitude is going to be given for inelastic scattering fudge factor e to I delta delta L minus 1 over 2ik. Then we make use of the Euler formula, so just write everything out. Eta cos 2I delta L plus I eta L sine 2I, not 2I, there's no 2I there, just 2 delta L minus 1, say 1 over 2ik. So this gives you 1 over 2ik eta L sine 2 delta L plus I 1 minus eta L cos 2 delta L. Then you just plug this into the expression. F of theta is given by the sum of these FLs. So you get F of theta is going to be 1 over 2k sigma L of 2L plus 1. Then you plug, this is FL, so you get eta k sine 2 delta L plus I1 minus eta L cos 2 delta L. Still have to multiply this by PL of cos theta. This gives you, and then once you square this, then this will give you the total cross section for the inelastic case. So let's just summarize. So you know that sigma for the elastic case will just be 4 pi sigma 2L plus 1 FL squared. So this just gives you pi over k squared 2L plus 1, and we determine what that would be, so it's just 1 over eta L squared minus 2 eta L cos 2 delta L. And similarly, sigma inelastic will be pi over k squared sigma 2L plus 1 of 1 minus eta k squared. And then you can try to do the same or try to prove the optical theorem in the inelastic case. So that will involve you looking at f of 0. So change column. You can check that the imaginary part of f of 0 in the inelastic case given by 2L plus 1, imaginary part of f of the partial scattering amplitude. It simplifies to 2k sum L from 0 to infinity 2L plus 1 minus eta k cos 2 delta L. Now, if then you consider the case of total absorption, as I said, for total, say, I think this might be an example that I considered. Okay, let's just look at the slides. Yeah, so I gave you so in an experiment you had pions scattered from a heavy totally absorbing nucleus, radius 1.4 Fermi. Estimate the total elastic and inelastic scattering cross sections. So because it's totally absorbing, so okay, maybe I should start by writing on this slide. Because it's totally absorbing, that means that fudge factor eta L is 0. So in this case, sigma inelastic just be given by pi over, once you set eta to 0, the equation then simplifies into L equals to 0 to infinity, but I'm not going to sum all of them, so you get to L max. This is just, there might be a cutoff which I will call L max, which I still have to try to determine. Of the formula just simplifies to 2L plus 1. L max given by Ka. So which again we don't really know. So this just gives you, I think I'm doing, this is probably, yeah, I think I'm discussing this one, but it will be the same types of formula. So meaning that sigma max, sigma in elastic is going to be given by pi over k squared, L going from 0 to Ka of 2L plus 1, which you can do the sum. It's just going to give you Ka plus 1 squared. And because we are assuming that Ka is much bigger than that 1, so then this just simplifies to pi over k squared of Ka. Missing a factor of k, but this just gives you pi, and we're squaring that. No, I'm not missing a factor. I'm just saying that Ka is bigger than 1, so ignore that. So you get k squared, a squared, those cancels, and then you just get pi a squared. And this is just scattering off from a disk. And it's the same expression for, you can check that this is the same expression for the elastic case. So the sigma total will be the sigma that you get from the inelastic case plus the sigma that you get from the elastic case, and this gives you 2 pi a squared. And this is not classical, because classically it was just scattering stuff there, but because the particles might be behaving like waves, they might diffract, and then by using Babinet's principle from optics, that other effect from the diffraction of the particles with matter duality, that will give you an extra pi a squared. So the 2 then is just a quantum mechanical effect. Then we can try to do this one. Just that these formulas are the same because it's totally absorbing, so we set eta to be 0. Okay, let me just try and delete and put question. Okay, so we have pions scattered radius, estimate total. So to get the total, we first need to find f of theta. Not 135. Calculate, estimate, calculate total cross section. 6 estimate the total elastic. Okay, so we might be using the same formula, that sigma elastic for totally absorbing will be the same as I can't see where I did this problem. Just think of theta. For theta, estimate 1 point scattered, 1.4 estimate total scattering. So I will first try to find what is f of theta from the expression I over 2k L equals to 0 until we get to L max, which is what I wrote previously, 2L plus 1 PL cos theta. But now I'll first have to try and figure out what is that L max. So that's what I did in the previous example. L max probably Ka. I I have that A there, but I still need to determine the K. K, I can get it from the energy, but I don't see the energy. Let me just try and see where I did this. Just give me a second. Um, I cannot see where I did this problem. Okay, I'll just type out the solution. I think for today we can end there. So, because I think we might have to finish by next week, so I might have to start recording pre-recorded lectures. So maybe tomorrow I'll give you. So this section on differential cross-section, I think we are done. So I'll start doing rotations in quantum mechanics and symmetries, but that will be pre-recorded, maybe during the weekend or maybe tomorrow. And then next week I'll try to finish by Friday. Are there any questions so far? So this scattering experiment, I'll type out the solution. Just cannot think properly. It's here somewhere. Just
Morning, doctor.
morning.
Sorry to bother. With regards to the semester test, you mentioned something in Tuesday's lecture with regards to question one, or the first part. Is the test going to count less than 70 now because of that question, or is it still going to count the full marks?
So when I said the question, I was thinking that when you wrote the exact eigenstates, those things counted half of the question. So everyone should be getting it counted for marks. But if you can get the only do the perturbative part of the problem, I think I was giving people 7 or 8. So
But also, so you in the question you only asked for the second order perturbation, you didn't ask explicitly to show the first order.
right. No, usually when I say 2-second order, I meant that you should first try to get the first order, which usually is 0, and then you
Okay.
then try to move on to this one. So it's just maybe I phrased the question very badly. I was saying that calculate to the first non-vanishing
Okay, so
order.
that's what you meant.
Yes.
Also, sir, with the exams and stuff, when are we precisely going to write it, or are the dates staying the same as on the calendar that was uploaded onto ClickUp?
I spoke to Prof. Theron, so he told me that the exam will be written on the 23rd.
So the dates didn't move from before we had that week break.
No. So those dates are still fixed. The only problem that I'm having is in terms of whether to set it out to be 24 hours. So there's a problem, which is why I've not even gotten to do much of the work. So some of you cheated on the exam, so they submitted the entire question paper on check.
Oh,
So, and
okay.
faculty already said that we should avoid giving students 24-hour exam because it takes the people from check, it takes them some time to write those solutions. So if I'm giving you a 24-hour exam, they have more than enough time to do the entire question paper, and then people just write those. And the funny thing is that they write the wrong thing, so it's like
Yeah, okay.
but I think the best solution is that the exam will be 24 hours. I think after writing the exam, then I'll try to go to see if anyone submitted the question paper on online.
But does it show who posted the question, or is it just a unknown?
There are two people who posted it there, so we were still trying to figure out with Prof. Theron as to how to
Okay.
deal with that matter.
Okay,
But
thank
I
you very
don't
much,
think that
sir.
it would be fair to punish other people for what other people did. So just that, I think for the exam, make sure that you make use of Griffiths and uh, maybe the lecture slides because I've not really been following Griffiths. Other than
Okay.
that, don't to Google or use check.
Okay,
Then the
yeah,
exam. Right.
yeah. Okay. Thank you, sir.
Okay. I can't find where I did this. So I think I'll just type out the solution, then post the updated slides later on during the day. I think we can close the session then.